Hi there. This video is to look at the maximum range of a projectile. So take for example the javelin thrower that's pictured there. They throw a javelin and you can imagine that it goes up into the air in some parabolic trajectory and then hits the ground again. We're ignoring things like air resistance. So the question is, what angle, let's call that theta, will maximize the range, which I'll call r? And does that depend on the speed? Is there a different angle for different speeds? Well, let's think about first of all a few different limiting cases. So first of all, you could think of the case where the angle there is 90 degrees and the javelin is thrown straight up in the air. So it goes up into the air, it turns around, it comes back down, and the javelin thrower does not have a good day. So there, r is 0. The other case is if it's thrown straight along the ground, so theta equals 0. So the angle is 0. Well, because of the weight of the javelin, it will immediately hit the ground. Okay, so we're making some assumptions here. We're ignoring the height at which the javelin is thrown from, which would be about a meter and a half above the ground. So we're ignoring that to say that the range there would be 0 as well. So the domain of this problem, the possible values of theta must be somewhere between 90 and 0 degrees. So let's investigate it a bit further. We're going to use the Suvat equation. In particular, we're going to use this one. S equals ut plus a half at squared. So in this equation, S represents the displacement, U represents the initial velocity that the javelin is thrown at, or whatever the projectile is, T is the time that has passed, and A is the acceleration due to gravity. So we're going to resolve this in different directions, and what we're going to do is we're going to take upwards as a positive direction, and we're also limiting ourselves to the case where the projectile comes back down to the same level as it started at, which would be the case in to a good approximation for a javelin thrower throwing a javelin onto a flat field. And that allows us to say that the vertical displacement is 0 because it's exactly the same height as it starts at. If the initial velocity is u, then we can calculate the vertical component of that, which would be the sine component because it would be opposite the angle. So if the hypotenuse of the triangle is u, then the opposite side is u sine theta, and the adjacent side is u cos theta. So we can say that the velocity in the vertical direction is u times sine theta, and times t, and we've got acceleration which acts downwards. It's always towards the center of the earth. So let's write that as the acceleration is minus g. So we've got a half minus a half times g times t squared. So g is the 9.81, but I'll just leave it as g for now. Okay, so we've got an equation here that has the time as a variable, but also this angle we're interested in, we're allowing that to vary as well. U will be some constant, so there'll be a particular speed that we're throwing it at. Okay, we could fix that to a particular value if we wanted to, say 20 meters per second, but we'll just leave it as U. But recognize that that's a constant, and also G is a constant. But we've still got two unknowns, so we need a second equation. So let's resolve horizontally. So the horizontal displacement is what we call the range, r. The horizontal velocity from the triangle again is u cos theta times t. And there's no horizontal acceleration because the only force that we're considering here is the weight of the projectile, which acts down, not across. So we've simply got that. So what we would like to do is eliminate the variable t, the time, between these two equations. And there are a few different ways we can do that, but maybe the easiest way is to factorize the first equation So take out a factor of t from both of those. So we can see t times u sine theta minus a half gt. So that's equal to 0. So therefore we've either got t is equal to 0, which is obviously at the start, or we've got this bracket equal to 0. And if you rearrange that for t, you get u sine theta divided by a half of g. You divide by a half, that's the same as multiplying by 2, and then divide by g. So that's the time that the projectile is in the air for a given angle. So let's substitute that into the other equation. So we get u cos theta multiplied by 2u sine theta over g. So 2u squared over g, let's put all the constants together at the start, and then we've got sine theta times cos theta. So we've now got the range as a function of the angle. So how do I maximize that? Well, we know in maths that the way to maximize a function is to differentiate it and find where the first derivative is equal to 0. Now we could just apply the product rule here, because we've got sine theta times cos theta, but it helps, it makes it a little bit easier if we use a trigonometric identity first. So we know the double angle formula, 2 sine theta cos theta is the same as sine of 2 theta. So we're going to use that there. So we can see we've got a 2 and we've got sine theta cos theta. So we're going to replace that by just sine of 2 theta. Okay. So now we're going to differentiate this. So we'll say dr by d theta. So u and g are constants, so nothing happens with those. So we're just differentiating sine 2 theta, and we have to use the chain rule there. So sine differentiates to cosine. And because of the chain rule, we have to differentiate 2 theta as well, which is 2. So a 2 comes to the front. So there's the derivative. And if we want to find a turning point, then we set that equal to 0. And therefore, since u squared and g are just constants, we can say that cos 2 theta equals 0. And if we just remind ourselves of what cos 2 theta would look like, the first minimum on that is where the first 0 on that graph is where 2 theta is equal to 90 degrees. Okay, so the inverse cosine of 0 is 90 degrees, and therefore theta equals 45 degrees. Now the general solution to that cosine is going to have multiples of 360 added onto that, or when we divide it by 2, multiples of 180, but we're not interested in that because the domain of our problem is just 0 to 90. So this is the only one we're interested in. So the angle is 45 degrees, which you might have guessed at the start. So if you throw it at a 45 degree angle, in the absence of air resistance, you will get the maximum range of the projectile. What is that maximum range? Well, it will be u squared over g times sine of 2 times 45. 2 times 45 is 90, so sine 90 is 1. So it's just u squared over g is the maximum range. Finally, we should check that it is a maximum value that we've found. So how do we do that? Well, we use the second derivative. So we differentiate it again, and if you hadn't used the identity, then this was just a little bit more awkward. So just as well we did do that. So we differentiate this expression once again. So cosine differentiates to minus sign. So we get minus, and we get another 2 coming out, so we get a 4 at the front now. 2 times 2 is 4. So we get minus 4 u squared over g times sine 2 theta. And if we evaluate that at 45 degrees, then sine 2 theta again is 1, sine of 90 is 1. So we just got minus 4 u squared over g. In u is taken in this problem to be a positive value. Well, it doesn't really matter what it is because we're squaring it anyway. In g is a positive, that's 9.81. Okay, so that means that this constant here multiplied by the minus 1, that is a negative value. And if we've got a negative second derivative, then that shows that it is a maximum. If we do include air resistance, then that actually lowers the angle. So in a real situation, what you want to do is keep the javelin in the air for as short a time as possible. So it's actually less than 45 degrees if you have a real situation. Okay.